So, yesterday we looked at a bit of circle geometry because that's a popular one. The other popular one we see a fair bit of is in induction questions. I mean, you can get inequations or inequalities to prove in 3 unit, but they're probably more likely to be in a extension 2 paper, I suppose. So let's just do one of those to start off with, a bit of a warm-up. So we tested for n equals 1. So left-hand side, yes, that's 1. Right-hand side, oh, that's 1 as well. The thing to get, or not get hung up about here, is that making the statement left-hand side is less than or equal to. Think about what you're saying. You're saying it's less than or it's equal to. Well, it's equal to. So yes, it is less than or it's equal to. No, you cannot set it out this way before I go any further. This is to save a bit of time, okay? No, you do not set it out this way. So our assumption for n equals k, we want to prove for k plus 1. Okay, let's do the proof. It's a series type, so using the idea of sum of term k plus 1, we'll sub in our assumption, and I get less than or equal to 2 minus 1 on k plus 1 on k plus 1 squared. Well, I'm not going to muck around with a 2. I mean, it's already there. So it's stupid to put that into the fraction only to pull it out again later on. It's a waste of time. How about I create an algebraic fraction though? But be careful when you create this one, because I'm saying minus the whole fraction. So that second fraction, the numerator becomes minus k. Common mistake there would be to go plus k, and then of course it stuffs the whole thing up. All right, we're trying to get, what was the denominator again? K plus 1? So clearly on the top, what we would like would be k times k plus 1, then that will cancel nicely. So let's see what we get. K squared plus k plus 1. Close. If I separate that into 2 fractions then, the first fraction is what we actually want, because that will factorise to be k plus 1. But then I've got this other annoying thing left over. But of course, that's the beauty of it being not an equation, but an inequation, because if I subtract something from these first 2 terms, it of course has to be smaller than it. So this line is less than just the 2 minus k on k plus 1 on k plus 1 squared, which cancels to what we want, and voila, we have our solution. All right, so we have seen ones like that before. The ones in extension 2 that we probably haven't looked at yet are the ones that involve recursive formulas. Okay? So a recursive formula, that's simply when you define the term in terms of its previous ones. Now we have seen them, we hadn't used it a lot, but if you think about it, arithmetic progressions, geometric progressions, we could write as a recursive formula, because you could say for an arithmetic one that term n was equal to term n minus 1 plus the difference. So that would be creating a term from using previous ones. If it's defined by more than one preceding term though, so I'm just saying, well, let's say it's defined by m preceding terms, then really what we need to do is to prove it true for the first m terms, so not just the first one. So however many terms are in your definition, prove it true for that many. And then assume it true for that many as well. Okay? Because you're going to end up using that formula as part of your proof. So you have to be able to assume that all these things that you're going to sub in are correct. But what you don't do, and this is a mistake I see happen, don't try and prove the recursive formula. Okay? That's given to you as a fact, so you're allowed to use it. That's not what you're trying to prove, the recursive formula. So let's look at a simple one here. This sequence, the first term is the square root of 2. Every term after that is going to be the square root of 2 plus the term before it. We have to show that every single term in this sequence is less than 2. So, yeah, there's only one term in the definition, so that's an, so I only need to test for n equals 1. They told me term 1 was the square root of 2, and sure enough, the square root of 2 is less than 2. So my assumption is going to be that term k is less than 2. I want to prove term k plus 1 is less than 2. So, proof. Well, it's usually a good idea to start with the recursive formula. So ak plus 1 is equal to the square root of 2 plus ak. But we have assumed that ak is less than 2. So therefore, our term is going to be less than the square root of 2 plus 2. And the square root of 2 plus 2 is the square root of 4, which, what do you know, is 2. Voila! So term k plus 1 is always less than 2. A simple little induction there to do. Here's one a little bit more interesting. We've got two different sequences happening, and they sort of are connected to each other. So we've been told the first term in both of them. So for the x sequence it's 5, for the y sequence it's 2. Then our recursive formula for the x sequence is we get the term before it in the x sequence, but also the y sequence divided by 2. And to get the next term in the y sequence, we multiply the two together and divide by that. So let's see what happens. We're going to prove that it doesn't matter which ones we pick, it's always going to equal 10. So we'll test it for n equals 1. And, well, sure enough, 5 times 2 is 10. So it works if we grab the first one from each sequence. We're going to assume then that xk, yk is 10. We want to prove that xk plus 1, yk plus 1 is 10. Going to start with our recursive formula. So xk plus 1, yk plus 1 will be those two things multiplied together. And you'll see that actually what looks very interesting is actually very boring. The xk plus yk cancels, the 2 cancels. Oh, what do you know? There you go. Oh, it's always 10 there. Okay. So, all right, so that one works. Let's play with Fibonacci numbers. They're always fun. So the Fibonacci sequence, of course, you're given the first 2 terms. The classic Fibonacci sequence. Yeah, so 1, 1, and then we get each term by adding the 2 previous terms together. And the lovely pattern we got here is that it's always less than 1 plus root 5 on 2, which is, of course, yes, but it is the golden ratio, but it's the irrational number pi. There you go. See, pi gets all the credit. Phi is a good irrational number as well. But that's 1 plus root 5 on 2. And everyone's going, oh, of course, we do that. Now, in this case, if you look at the recursive formula, it's defined by 2 previous terms. So therefore, I need to test it for 1 and 2 as well. Which, well, term 1 is 1. And 1 plus root 5 on 2, as I said, 1.6. Well, actually, I think it goes 1/8 after that. I think it's 1/8. Anyway. But anyway, it is less than, 1 is less than 1.62. So it works for the first term. Second term, which is also 1, but now it's 1 plus root 5 on 2 squared. That's 2.62. So yes, it does work for both of those. So now we're going to make 2 assumptions. So 1 for k minus 1, 1 for k, which will allow me to use the recursive formula for term k plus 1. We want to show term k plus 1 is less than 1 plus root 5 on 2 to the power of k plus 1. Okay, so there's the recursive formula. Sub in my 2 assumptions. We have to somehow turn all this into 1 plus root 5 on 2 to the power of k plus 1. So I'm going to factorise out what I want. See, I know normally when you factorise you take out the lowest power, but I'm figuring it's going to be easier to show those square brackets is 1 or less than 1 or something like that. So, because I've got what I want, I now just have to play with the square brackets. Okay, well, the reciprocal of 1 plus root 5 on 2 is 2 on 1 plus root 5. And square it, we get 4 on 1 plus root 5 squared. That has a common denominator of 1 plus root 5 squared. Top of the fraction becomes 6 plus 2 root 5. And you'll never guess what 1 plus root 5 squared is. It's 6 plus 2 root 5. So in fact, yes, it does work for that one. All right. So the main difference, I guess, with extension 2 ones is often, or not often, but sometimes you see these recursive type of induction questions.